Hi! In this video we explore some examples of curves parametrized in different ways, rational parametrizations among them. The examples will be the circle, the hyperbola, and the lemniscate of Bernoulli. We begin with the circle. The circle of center C and radius r is the set of all points P on the plane such that the distance from that point to the center is r. When we use coordinates, this condition is the one at the right-hand side on the screen. We work now in the case where the center is the origin, the point 0, 0. From the equation, we can solve for y, so that for a value x0, we get the corresponding value of y0. For another value x1, we get its corresponding value y1. And in general, for each x, the expression of y is the square root of r squared minus x squared. Note that this parametrization only covers the upper semicircle. We saw in a previous video that the trigonometric functions sinus and cosinus provide another parametrization of the circle, in this case of radius 1. The parameter is the angle defined from the horizontal axis. We can contract the parameter by dividing it by 2, and even though the parametrization changes, the trace is the same. And this new parameter has a geometric interpretation. The parameter A is the area of the circular sector defined by that angle. Another parametrization of the circle is as follows. In this case, we work with the slope of all the lines passing through the point minus r0. Each of these lines cuts the circle in a second point. We avoid the vertical line. For each slope, we get a point in the circle. For every point of the circle of coordinates x and y, the slope of the line joining that point with the point minus r0 equals y over x plus r, and the explanation comes from that green triangle on the screen. We now work the equation of the circle together with the equation of the slope. The idea is to get the expression of both x and y in terms of m. Some algebraic manipulations, those you have on the screen, finally gives two possible values for y. The value 0 and the expression at the end of the slide. The value y equals 0 corresponds to the origin of the pencil of lines. And the other is the expression we are looking for. And from it, we also get the coordinate x of the point. That gives the parametrization of the circle in terms of the slope. Note that this parametrization is rational, as it is written as a quotient of polynomials. We have a special point, the origin of the pencil, and the others are parametrized with respect to the slope. And which is the domain of that slope? The domain is the full real line, that is, from minus infinity to infinity. There is a relationship between this rational parametrization and the parametrization using trigonometric functions. If we let m be the tangent of alpha over 2, we go from the first to the second. The geometric interpretation of this change of parameter is the one given on the screen. Roughly speaking, we now have three parametrizations of the circle, each of them with a different geometric interpretation. We now study the second example, the hyperbola. This is the locus of points for which the ratio of the distances to a given point f and a line is a constant e. For e equals the square root of 2, the equation of this set is x squared minus y squared equals 1. As we did with the circle, we can solve y from this equation. We thus get the parametrization of the upper part of the two branches of the hyperbola. For a second parametrization of the hyperbola, as we did with the circle, we are going to use the area of the region defined from the horizontal axis. That area is the blue region on the screen. We can work much better with this blue region if we rotate the hyperbola 45 degrees. If we call u and v the new coordinates after the rotation, the equation of the hyperbola is very simple. U times v equals 1. Both coordinates x and y and u and v are related by means of a matrix on the screen. Or these other expressions at the bottom of the screen. For a point uv, we compute the blue area as follows. It is the sum of two green regions, A1 and A2, minus a red region, A3. We compute the area of these regions. The first green region is a triangle of area 1/2. The second is the area of the region defined by the function 1/v and can be thus obtained as a definite integral, the one on the screen, and that integral gives the logarithm of u. And with respect to the red region, it is again a triangle of area 1/2. From these computations, we can give the value of the blue area, and it is just the logarithm of u. From it, we obtain that u is the exponential of a, the area, and v, being its inverse, is the exponential of minus a. Rotating back to the original hyperbola, we get the expressions for x and y in terms of the area of the blue region. These expressions are combinations of exponentials, as those we have on the screen. These combinations are called the hyperbolic cosinus and sinus, following the spirit of the second parametrization of the circle before in terms of the area. Summarizing, the parametrization of the right branch of the hyperbola with hyperbolic trigonometric functions is the one that appears on the screen, with agreement that A is negative when the area is measured counterclockwise. By symmetry, changing the sign of the hyperbolic trigonometric functions, we also obtain the parametrization of the left branch. Finish this video with the last curve, the lemniscate. This curve is a set of points such that the product of the distances to two fixed points is constant. The polar parametrization of this curve was given in a previous video, and you have it now on the screen. The angle theta is the angle with respect to the horizontal axis. The implicit equation characterizing the points of the lemniscate is the polynomial that you have now on the screen. You also have the parametrization. It is again a rational parametrization. The student can easily check that the coordinates of this parametrization satisfy the polynomial. The relation with the polar parametrization is given by the relation t² equals the tangent of p/4 minus theta.